So with that background, my department was appointed by the Department of Science and Technology, the government department, to engage in two particular housing projects, low-income housing projects in South Africa. One in Mdantsane, where we're looking at 500 houses, which is that over there. That's what we saw when we got to actually visit the particular development. 16 million rands worth of road had been washed away because it was the wrong solution, and that is what they called a house. And in Kleinmond, where we were faced with this circumstance, to engage in the development of 600 houses. And the challenge we were asked was the following: to develop, test, and implement innovative technologies aimed at improving the performance of the houses. For what purpose? To contribute towards sustainable human settlements. Understanding 2.2 million of these houses need to be built, and in fact, we are creating unsustainable human settlements. And so what we did was to look at the standard condition. It's a 40 square meter house. That's roughly a 400 square meter house. It has to be built for less than $8,000, typically built from a concrete masonry unit, a single skin. It has a slab, it has a steel roof sheet, no insulation. So the temperatures inside that building go between -10 and +40, depending on the particular climatic condition. It gets a single electrical board with 2 light plugs and 1 light point, a single light point in the kitchen. So if you want to get up at nighttime to go to the bathroom, you cannot do that. It has no hot water. And as a consequence of the way these things have been developed by government, 16% and 14% respectively reported weak walls and roofs in these structures. 30% in the Eastern Cape and Western Cape, which are coastal conditions, reported problems with walls and roofs. So the units that are being developed to solve a problem were in fact creating another set of problems. So the challenge we set ourselves was this: how and in what way can innovative material production and assembly technologies in science engineering technology be applied to construction manufacturing to improve building performance, construction processes, and here's the catch: lead to sustainable human settlements. I then built on our site a collection of buildings. These three, industry came and participated with those two, but I built what government typically develops in South Africa as a 400 square meter, $7,000 house, which is the one over there. And we monitored that construction process. We then built exactly the same house, which is that one, to the standards of the house that I live in South Africa. And the research challenge was, is it possible for us to build that quality of house for the same amount of money? Because I think people should be living in that house, not that one. But government hasn't got the money to pay the extra. And so we developed that one, which is this house over here. And in order to do that, we pulled the house apart across 5 categories: the substructure, the superstructure, which is the walls, the windows, and the doors up to the roof assembly, the services, and the finishes, and analyzed each one for opportunities to explore performance adjustments. Now, what we had done in the meantime is the CSR had developed an ultra-thin concrete road, which is this one here. It's 50 millimeters thick. It's carrying trucks, and it's being laid in the townships around South Africa. And so I figured, you know what, if they can drive a road on it, drive a truck on it, I can build a house on it. So I actually went and did a piece of road. What this meant was that I didn't have to use foundations, I didn't have to excavate, I didn't have to bring in any material. I used the local material, and we built a platform to build on, which is in fact much stronger than what the builders typically do. 50 millimeters thick. We then looked at the superstructure and watched how the contractor was building that wall, and looking at the degree of wastage as he had to break blocks to make them fit. And in order to resolve that, I actually developed a Lego system of blocks that resulted in a zero waste house. There's not a single block in this building that gets cut. And they simply put it together like a series of Lego buildings, Lego blocks. We then looked at the roof. I needed to get an overhang on the roof to provide sun shading to the east and west elevations. And in order to do that and keep the roof running in the conventional direction, I would have had to put an additional layer of timber to change the roof shape. And I couldn't afford that, so I changed the roof sheet and tilted it from the front to the back so that the entire roof is in fact acting like a gutter. And watched it when it rained. And you can see how the drip line increases here towards the corner. And that's where we went and put the rainwater tank. So the roof is in fact discharging the water straight into the rainwater tank. Then looked at the services. That is a typical plumbing installation in a low-income house. A whole lot of pipes, all of them exposed. And we rationalized that into this system. 46% saving in plumbing just by, in fact, designing a manifold system, grouping the services together so that you could do this off-site. We trained the local community how to build that plumbing system. Mommies and daddies were sitting under a tree gluing these pieces together. And we pressure tested it. If it failed, they had to do it over. If it didn't fail, it got installed. So we created a whole series of jobs around creating plumbing manifolds, 46% saving in plumbing. I looked at the shower base. And so we installed a little plug in the shower base so that you can, in fact, fill it with water. There's a solar water heater on the roof that provides hot water for this. So you can, in fact, now bath baby, which you couldn't do before. We looked at the finishes. Typical finish in a low-income house is a cementitious covering that provides no real protection to the weather elements. In fact, you can see the damp line appearing on this construction. And developed in partnership with private sector a plaster coat that has a volcanic material in it that's in fact providing additional thermal performance. And then what was quite interesting is we set ourselves the task of measuring whether we in fact would get any performance improvements to meet the research question. So we did some energy modeling on our house. And the typical government house would require a 12.29 gigajoule heating load and a 7.5 gigajoule cooling load to maintain a temperature between 18 and 22. So it was a total energy load of 18, 19.7 to 8, almost 20 gigajoules. Due to the interventions that we put into our house, we managed to reduce that by half to 8.86 gigajoules on a 400 square foot structure. We then did a life cycle analysis on the materials. And the house that we developed uses 35 less material resource input by weight than a subsidy house. So for every 2 houses that government is currently building in material weight, we can build 3. Because we eliminated so much of the concrete work, the thin concrete slab and the foundations, we have a reduction of 685 kilogram equivalents of CO2 loading, which has almost a ton of CO2 on a 400 square foot building. And it contributes less to water depletion because of the reduction in water. And this then led me to think, how can we begin to roll this out in a way where green building and green design can assist government in meeting its national imperatives? Because if we're showing these savings, then government can in fact achieve more with what it's doing than it's currently doing. So I took that house and I escalated it up to the 2.2 million. So if we look at the energy reduction in heating and cooling per house at a national scale, would save government 23 million gigajoules in energy that it would not have to generate. That in turn would save 1.4 million tons of carbon dioxide because of the reduction in both cement and energy use. Would save 39 million tons of material, 41 cubic meters, million cubic meters of water. We would harvest 46 million cubic meters of water through rainwater tanks. The scale of taking simple little interventions and escalating it up to meet national imperatives is just enormous. A total CO2 reduction in excess of 4.4 million tons. And at the same time, delivering a quality of life improvement. So we rolled this out. That is what they were getting in Mdantsane. That's the house that we're currently building. And we put every single site under scrutiny to make sure that over time they can expand that house into a fully fledged building. Umtunkulu village was a demonstration project. That is the house that was built down there instead of the normal one. And in Kleinmond, whereas that is what they're getting, this is the project we're currently busy with. We are building 411 of these houses. And so it makes me think that we cannot continue to treat sustainability as a separate measurable deliverable, either in education or in practice. If green buildings are to gain credibility, they must include respect, perhaps even reference for the multidimensional evolving potential of the human experience, Maslow's hierarchy of needs, way beyond the indoor and external environment experience. We have to resolve Kingsley Davis's challenge and Rachel Carson's challenge. Thank you.